Alright, good afternoon everyone. So in today's class I would like to discuss about boiling heat transfer. But before we start our discussion, I want to show you this video. Okay, so this video is a Fukushima nuclear disaster. So if we recall the incident of Fukushima nuclear power plant, the explosion happened on March 2011, which is around 8 years ago. And this incident, it led to the occurrence of earthquake and also tsunami. Okay, so now, do you know what caused this explosion? Any idea? Anyone? Nice guess. But would you believe that a simple phenomena has caused this devastating explosion? Believe it or not, boiling played a crucial role in this incident, and that we are going to tackle for today. Okay, so now, all of you here, you are going to be a future engineer, right? So as an engineer, it is our job to design, to develop, to build a system with a good quality, good security, and of course the safety. Okay, so now, we should always surround ourselves and put a big question in our head, like, what's this? Why it happened? And how we are going to solve this problem? Okay, so before we build or before we design a system, it is crucial to have a deep understanding of the underlying mechanism or phenomena related to our project or related to our work. Okay, now like in the case of the nuclear power plant, understanding boiling mechanism, boiling phenomena, boiling process, it's fundamental to achieve a good result and secure the safety. Now let me ask you, what is boiling? Alright, boiling is the formation of bubble due to the heat addition. So in this case, boiling is classified into two, pool and flow, and it depends on the presence of the fluid motion. In the case of pool boiling, the fluid is stagnant, static, and in the case of the flow boiling, the fluid is forced to move in the heating pipe. So normally we use pump to do this. Okay, now let's focus on the physical mechanism involved in pool boiling. So to understand this boiling process, this boiling mechanism, let's consider an example, a chamber containing some water and placed on a burner. Okay, so yeah, exactly. It's just like when we boil water in the house, we place the water on the pot and then placed it on top of a stove. So what happened? When we start to heat the water, the heat transfer from the bottom of the chamber into the fluid, and then it start to rolling up and down. So the hot water will rolling up and then the cold water will roll down. And then the bubbles start to generate on the heated surface. And after some times, the water gets boiled. And this process, we call it as pool boiling process. And in this pool boiling process, there are 4 different stages, which are free convection boiling, and then nuclear boiling, and also transition boiling, and last is field boiling. And these 4 stages can be easily plotted on the heat flux and temperature difference. So let's plot. Okay, this is the plot. In this plot, the x-axis represents the delta T-axis, or the temperature difference between the wall temperature and also the fluid temperature. For the wall temperature is the temperature of the chamber, okay? And then for the fluid temperature, as we use water here as the fluid, and then the temperature is under the saturation temperature. So for the water, saturation temperature will be, okay, correct, 100 degrees Celsius. And for the y-axis, it represents the heat transfer to the fluid per unit area of the chamber. We call it as heat flux or Q dot. So this curve, the OABCDE, we call it as pool boiling curve of water. Now let me explain the first stage, which is the OA or free convection boiling. What happened here? So when we start to heat the chamber, the heat transfer from the chamber into the fluid, into the water. So in this case, there is a natural convection, like the one that I explained before, the rolling up and down, the hot water will go up and then the cold water will go down. So that process is a natural convection. So this natural convection is induced the increasing of heat flux and also the delta T. So in here, it starts to increase the heat flux and also the delta T. So after the water reaches the saturation temperature at 100 degrees Celsius, because if we continuously heat the chamber, the temperature of the chamber became higher than the temperature of the fluid. Then the boiling started. There is bubble generated on the heated surface. And this phenomenon, when bubble generate on the heated surface, we call it as ONB, or onset of nucleate boiling, which is at this point, point A. Okay? Okay, now let's move to the next curve. The next curve is ABC, which represent the nucleate boiling. In the nucleate boiling regime, we divide it into two regimes, which are AD and then BC. In the AD regime, we call it liquid entrainment. The delta T keep increasing, and then the bubbles start to generate on the heated surface. When the bubbles start to generate on the heated surface, the bubble will grow in size, and then it will detach from the heated surface. When it detaches from the heated surface, the bubble will rise up, and then it will collapse. After a few distance from the heated surface, it will collapse. This collapsing bubble, we call it liquid entrainment. And then this collapsing bubble, because it's collapsed, it makes a disturbance on the fluid. Because before the fluid is stagnant, right? It's just static. And then there is a collapsing bubble. So it makes a movement in the fluid. It disturbs the fluid. And then this disturbance, it's induced of the increasing of the heat transfer. Anyone know heat transfer coefficient formula? Let me write it. So heat transfer H equal to heat flux divided by delta T. So as heat transfer coefficient increase, automatically the heat flux also increase. So there is an increasing of the heat flux in here until it reaches the maximum heat flux in point C. Okay, now let's move to the curve BC. Because of the continuously heating on the chamber, the bubble that generate on the heated surface now not just individual bubble. It becomes more bubble generated on the heated surface, and then they generated faster than the previous bubble which generated on the AB region. Okay, so in this case, because there are many bubbles, the frequency rate high with the velocity also high, the bubbles start to interact with each other. So like this bubble, and then another bubble generate just beside this bubble, and then they will interact with each other. They will merge, they will coalesce with each other, and then this small bubble, and then they merge, they form bigger bubble, and then it detaches from the heated surface, and then goes up and break up, collapse, right? So this phenomena, this process from the bubble generate and then they will interact with each other, it induces the heat flux to increase until it reaches the maximum heat flux, the point C. This point, we call it also critical point or critical heat flux or CHF. This point, point C, we also name it as the end of the nuclear boiling process, or the maximum of the heat flux, or the upper limit of the system that we design or the system that we build. Okay, so now let's move to the next curve. Curve CD, the transition boiling. In this stage, because of the continuous heating, the delta T keep increasing beyond the critical point. In this case, the bubble generated, the one that coalesced with each other and form bigger bubble, it became vapor film. And then this vapor film act as an insulator. And then this vapor film, it has a lower thermal conductivity than the water. So because of the thermal conductivity is lower than the water, the heat flux start to reduce until the maximum, until the minimum point of heat flux, or we call it also as a Leidenfrost point. Okay, now let's move to the next curve. Next curve is the DE or the film boiling. So the vapor film previously, the vapor film, the one that act as an insulator, it grew and then it became stable, and then it covered most of the area of the heated surface. So this vapor, it obstruct, it hindered, it's prevent the fluid to have a physical contact or to replenish the heated surface. So the heated surface, it became hot at high temperature continuously because the water cannot replenish the heated surface because of the occurrence of the vapor film. So there is radiation heat transfer due to the occurrence of the vapor film that cover the entire heated surface. Okay, until here, any questions? If no, then I'm the one who will ask you. So, based on this whole boiling curve, after I describe each stage, now I want to ask you, which stage among all of this is the critical or is the important stage in this curve? Anyone know? Very good. It's a point C, because this point, it represents the maximum limit of the heat flux, also represent as the upper limit of the system that we design. So when we design something, when we build something, we should know how much is our limit, how much is the critical heat flux of our system. Okay. Now let me take you back to the Fukushima nuclear explosion. This video, it will show you the factors that triggered the occurrence of the Fukushima nuclear disaster. What really the problem? What is the main problem caused the explosion? As we can see here, there is a failure cooling system, right? And then because of the failure cooling system, there is a reduction of cold water, and then the pressure will increase, and then because of the increasing in the pressure, there is a dry out and then overheating, and then because of the overheating, the corium start to melt down. And guess what next? After the corium start to melt down, boom, there will be an explosion. Okay, so now as an engineer, as we can see here, actually the main problem is because of the overheating. So we should know how to solve this problem. We should know how to predict the CHF, the vapor behaviors. What is the CHF mechanism? What is the factors trigger the CHF? And another solution is moving the reactor from land to ocean. Anyone knows why we should move the reactor from land to the ocean? Alright, because in here, there is a reduction of cooling water and failure in the cooling system. If we move the reactor from land to ocean, we have plenty of water, which can help to cool down our system. So there will be no failure in cooling system, and we will not run out of cool water, right? But when we move the reactor from land to ocean, there are another factors that might affect the system. Guess what's that? The movement. Because when we place the reactor in the land, it's just static, right? It's just diam. But when we move the reactor to the ocean, there will be effect from the waves, the ship motions, wind, and everything. So that's we are going to that we need to analyze more about another factors. Okay. So now how we are going to make this to predict the CHF and everything. Actually, there are many researchers already studied about this. They studied about boiling, they studied about the critical heat flux and everything, and they developed some correlations here. This correlation is to predict the nucleate boiling. Rosno and then Zuber also developed correlation to predict the critical heat flux and minimum heat flux at later frost point, and then Bromley develop this correlation to predict heat flux and the film boiling regime. So you can find it easily in this book, heat and mass transfer, or you can find easily from the internet about this. I will not give you a clue. So this is gonna be your homework to find about pool boiling or about the formula, and then it's just simple, right? You can just make another correlation. Who knows? This book is a 4th edition. Maybe in the 20th edition, I will find, like, what is your name? Sorry. Okay, Sarah's correlation to predict the critical heat flux of the nuclear power plant, right? I don't want to boast, but I also develop a correlation to predict a critical heat flux of ocean nuclear power plant. So in this case, we move already the reactor from land to ocean. Okay, I think I'll end this class. So if you guys, some of you are interested to know more about boiling, to know more about nuclear power plant, or you plan to have research for your final project, for your script C in this topic, you can just contact me and maybe we can have experiment, or maybe we can play together with some bubbles. Okay? Alright, see you next week on the next class, and please read about this so we can apply this formula into the system for next meeting. Okay? Thank you.